We now move into the first of several lessons on the general topic of classifying chemical reactions. Okay, so, biologists like to classify every organism by a rather complex classification scheme. We're not going to come up with quite as complex a classification scheme for reactions, but we would at least like to make some sense of the vast number of processes that can happen that are known as chemical reactions. Okay, so when you see a chemical equation written out that describes a chemical reaction, you should ask yourself, at least mentally, the following three questions. Okay, so the first question is, are the reactants both elements, both compounds, or is there one element reacting with one compound? Secondly, are the reactants pure substances, or is the reaction taking place in solution, or specifically in aqueous solution? And then third of all, what kind of reaction is taking place? Okay, so to answer this last question, we have developed a classification scheme, which is actually a three-step process. The first step is to classify the reaction as being either a combination, decomposition, single replacement, also known as a substitution reaction, or a double displacement, which is sometimes referred to as a metathesis reaction. We'll see some examples on the next slide as to what the definitions of each of these four reaction types are. Step two, if it is a double displacement reaction, which many of the reactions you're going to see in this course are actually going to be, we can then classify it further as being either a precipitation reaction, a gas-forming reaction, or an acid-base reaction, and we'll get into the details of what these terms mean in subsequent lessons. Do note that these terms will sometimes apply to single replacement reactions also, especially if they're taking place in aqueous solution. And then finally, on the third level, no matter what type of reaction it is, we have to decide whether or not it's a redox reaction. Redox is short for an oxidation-reduction reaction, and we'll have a lesson in which we understand and unpack what this term means and figure out what clues to look for to decide whether a reaction is a redox reaction or not. Okay, so first our definitions of the four classes of reactions. So I'm starting with the most general definitions, and then we'll look at specific examples of each of these reaction types. So for a combination reaction, this is simply two chemicals. Let's call them A plus B. They combine together to form a more complex product, which we're going to call AB, where all of the atoms in the two starting materials are incorporated into the product. A decomposition reaction is in essence the reverse of a combination reaction. In this case, we have a more complex reactant, call it AB, and under certain conditions, which frequently involve heating, AB is going to break apart to give two simpler compounds, which we're calling A plus B. Again, no atoms are gained or lost in this process. A single replacement reaction is usually going to be a reaction between an element and a compound. So A would be the element and BC would be the compound. And in this case, we start out with B bonded to C and A by itself. So A and B are going to switch roles in the products. So in the product of this reaction, A is bound to C and B ends up by itself. And then finally, in a double displacement reaction, we're starting out with two reactants that are both compounds and they switch partners. Okay, so initially we have A bound to B and C bound to D, but then after the reaction takes place, A ends up bound to D and B ends up bound to C. Okay, so as promised, some real examples of these reactions. First, we'll do a combination reaction, and that would be solid sodium oxide reacting with gaseous carbon dioxide to give solid sodium carbonate. Again, all of the atoms present in the starting materials are present in the product. For a decomposition reaction, I'm not doing the exact same reaction in reverse, but I'm doing a very similar reaction in reverse. In this case, we're starting with calcium carbonate, which is good old chalk, and it can decompose into calcium oxide and give off carbon dioxide gas. So single replacement reactions are frequently going to involve metals. So in this case, if you take solid iron, and a good source of iron would be a NaL, and put it into an aqueous solution of sulfuric acid, H2SO4, if you leave it in there long enough, that NaL will actually disappear. So all of the iron gets converted into iron sulfate dissolved in water, so it'll be an aqueous solution. And then the other product of this reaction is hydrogen gas, H2. So you can actually see in the picture of this reaction little bubbles forming of hydrogen gas. And there, since it's a gas, of course, the gas particles are going to bubble out of solution. Okay, so again, looking at this equation, iron and H2 take each other's place in terms of which one is bound to the sulfate. So iron in this case is A, and then H2 is B. Okay, then for our final example, the double displacement reaction. So if we take an aqueous solution of sodium chloride and an aqueous solution of silver nitrate. Okay, so in this example, we have the aqueous solution of sodium chloride in the beaker, and we're adding the silver nitrate through the dropper. They're going to switch partners. So the sodium, instead of being partnered with the chloride, is now partnered with the nitrate, and the silver, instead of being partnered with the nitrate, is now partnered with the chloride. And the way we know that a chemical reaction has taken place here is you can immediately see a precipitate forming, because silver chloride is actually a solid and is not soluble in water, so it doesn't stay in solution. Okay, so incidentally, the single replacement reaction is also gas forming and redox, and the double displacement reaction, as we talked about, is precipitation reaction. Okay, so finally in this lesson, I want to go back to the examples we looked at lesson 1 in this unit and be able to answer these 3 questions about each of those examples. So the first reaction we looked at in its balanced equation was sodium metal reacting with chlorine gas to give sodium chloride. So sodium solid giving sodium chloride solid. So are the reactants both elements, both compounds, or is one an element and the other a compound? Well, the answer to this one is that they are both elements. Sodium metal and chlorine gas are both elements. Secondly, the question is, are they pure substances, or is the reaction taking place in solution? So what you need to be looking for here is, do you see an AQ anywhere next to either of the reactants? I don't. We know that sodium in its pure form is a solid and chlorine in its pure form is a gas. So this is a reaction taking place between pure substances. And then what kind of reaction is taking place? This is a combination reaction. Okay, you're taking 2 starting materials and combining them to give a product. And again, with the equation properly balanced, all of the atoms in the starting materials end up in the product. Our second example from lesson 1 also involves sodium metal, but in this case, instead of reacting with chlorine gas, it is reacting with liquid water. This is when we took the drop of sodium metal and put the chunk of sodium metal and dropped it into the water bath, and we actually saw some fire coming off with this. Okay, products of this, at least the chemical products of it, are aqueous sodium hydroxide and hydrogen gas. So in response to question 1, in this case, sodium is still an element, but H2O is, of course, a compound. So it's a reaction between an element and a compound. For question 2, they are still pure substances. Okay, so if water itself is the reactant, it's going to be a pure substance. If it's just the solvent for something else being the reactant, then the reaction is taking place in aqueous solution. So it is possible to have water as a reactant and the reaction not be in solution. And then the answer to our final question is that this is a single replacement reaction. Okay, so again, looking at the formulas, H2O can also be thought of as HOH. And what we're doing is we're removing the H from HOH and replacing it with an Na to make NaOH. And then we started out with sodium by itself and ended up with hydrogen by itself. Hydrogen is not always going to be the product of a single replacement reaction. It just so happened to be in the two examples that we have seen. Okay, so that's our big picture overview of classifying chemical reactions. So what we're going to do in the next several lessons is look in more detail at combination, decomposition, single replacement, and double displacement reactions. Again, giving you some of the clues as to what to look for. And then we'll also define further the terms precipitation, gas forming, acid base, and redox.